this video, we will be presenting our final year project, Real-Time Acquisition of Chromatic Derivatives for Signal Processing and Machine Learning Applications. Chromatic derivatives were introduced to provide a highly accurate and practical method for reconstructing band-limited signals from discrete samples. While Shannon's interpolation formula can theoretically achieve perfect reconstruction, it is not practical because the sinc function used in the interpolation decays slowly. As a result, accurate reconstruction would require an arbitrary number of samples. Alternatively, Taylor series approximations are local in nature, requiring only the values of the function in a small neighborhood. However, this method relies on standard derivatives, which become increasingly sensitive to noise as the order increases, making them infeasible for higher order approximations. Additionally, the error is unbounded and truncations of the series accumulate errors very rapidly. Chromatic derivatives were introduced to overcome these issues. Similar to Taylor approximation, CDs can be used to obtain the chromatic approximation of a signal. We can see that chromatic approximation is accurate over a longer interval of time than Taylor approximation for the same number of degrees. We also see that unlike standard derivatives, we can obtain CDs for a much higher number of degrees without a reduction in SNR. Chromatic derivatives contain important information regarding the signal characteristics, making them useful for various signal processing tasks such as signal reconstruction. However, current research has yet to fully explore their applications in real-time signal processing and machine learning. Towards this end, our project explores three applications: real time recovery of missing data in wireless sensor networks due to unreliable transmission using CDs, improving performance and efficiency of machine learning models used for audio spoof detection and seizure prediction using CDs, FPGA implementation of an end to end real time CD acquisition and reconstruction system. The first is a signal processing application related to wireless sensor networks. Wireless sensor networks, or WSNs, are interconnected nodes that exchange information of interest. They are used in many applications such as weather monitoring and pollution monitoring. However, a considerable amount of data is lost during transmission due to issues such as synchronization issues and network congestion. While there are methods to deal with this, the state of the art methods are either computationally expensive or rely on data from neighboring nodes. In many cases, the data streams are band limited and oversampled. Hence, the missing data can be reconstructed using the chromatic approximation. Our system consists of two stages. The data stream to be transmitted is first passed through a low pass filter to remove out of band noise. Afterwards, the received data stream is passed through a reconstruction module that interpolates the missing data using chromatic derivatives. Here, the data stream is divided into overlapping windows, and the CDs of each window are estimated using the least square fit method, which involves solving the given optimization problem. The missing data is then reconstructed using the chromatic approximation, after which the windows are combined by averaging the overlapping regions. We tested our experiments on two datasets, which were based on real world WSN data. We selected the cutoff frequency of the filter empirically by analyzing their spectrum. Higher cutoff frequencies enable reconstruction for higher missing probabilities, but at the cost of risking loss of information. The experimental results show an extremely high similarity between the original and reconstructed data streams. Our method outperforms methods based on traditional univariate interpolation techniques such as linear and spline interpolation and maintains low root mean square error for a missing probability of up to 65% for Intel Lab data and 30% for Moline dataset. Significantly, unlike other methods, the reconstruction error of our method remains consistent for each sample in the data stream, even under extreme conditions, including a maximum gap of 3.6 Nyquist intervals. Next, we will look at how CDs can be used for machine learning applications. Chromatic derivatives contain valuable information about a signal's characteristics, particularly its higher order temporal dynamics and local behavior. Despite their informative nature, CDs have not yet been widely used in machine learning. As part of our research, we explore their applicability in two key areas: audio spoof detection and seizure prediction. Let's begin with the audio spoof detection task. Audio spoofing attacks involve manipulating or synthesizing speech signals to deceive automatic speaker verification systems. These attacks typically include methods like text to speech synthesis, voice conversion, and replay attacks. For our work, we used the ASV Spoof Challenge logical access dataset. In this application, we treat chromatic derivatives as input features. Specifically, we compute CDs at the center sample of every 20 sample window across the signal. This results in an input shape of n by 48, where n is the number of such segments and 48 is the number of CD degrees we calculate. This matrix is then passed into a machine learning model. Regarding the model architecture, we adapted the RawNet2 baseline. RawNet2 typically begins with learnable sync filters, but we replace these with our CD computation and a 1D convolution layer. The result of the architecture remained unchanged. With this technique, we obtained notable results. While the model didn't perform as strongly for voice conversion attacks A17 to A19, it showed a marked improvement in detecting other spoofing attacks, specifically A7 through A16. We observed up to an 83% improvement in equal error rate and a 47% improvement in minimum TDCF, showcasing the effectiveness of CDs in detecting non-voice conversion attacks. Now, moving on to our second application, seizure prediction. Here, the goal is to identify patterns in brain activity that distinguish the pre-ictal state, the period leading up to a seizure, from the interictal state, which reflects more stable activity between seizures. We use two well-established datasets, the CHB MIT dataset and the American Epilepsy Challenge dataset. Our approach involved two steps. First, we verified the usability of CDs for this task. Then, we trained a model to classify preictal versus interictal brain activity. To begin, we performed an unsupervised analysis using k-means clustering. When using the variance of chromatic derivatives as features, we observed clear clustering between preictal and interictal states in both datasets. This approach was inspired by the effectiveness of using the variance of standard derivatives. On this slide, you can see two visualizations. The left plot shows clustering for the American Epilepsy dataset. The right plot shows clustering for the CHB MIT dataset in the 2-hour window leading up to a seizure. In contrast, when we used conventional time domain features, this separation was much less distinct. One key takeaway was that CDs were able to detect the preictal state approximately 5 minutes earlier than time domain features. Building on this, we trained an MLP model using the CD features and time domain features to classify brain states. The results were promising. Not only did the model achieve comparable accuracy to models trained on time domain features only, but it also converged 65% faster during training. This suggests that CDs not only capture meaningful information, but do so in a way that enhances model efficiency. Now, let's take a look at the FPGA implementation of an end-to-end real-time CD acquisition and reconstruction system. In the initial phase, we reproduce the existing design using MATLAB System Generator for DSP. However, this approach resulted in large, unreadable Verilog code and compatibility issues with recent MATLAB and Vivado versions. To address this, we redesigned the system using HDL coder blocks, focusing on two main components, the filter bank and reconstruction unit. We then moved to FPGA in the loop testing to validate the subsystem accuracy on hardware. For FPGA in the loop testing, we used the VCU118 Vertex Ultrascale board to run only the core part of the design called the design under test on real hardware, while the rest of the simulation remained in MATLAB. This allowed us to verify the correctness of the HDL code with actual FPGA behavior, providing more accurate validation than software simulation alone. The complete real-time system was implemented across two boards. Audio input was streamed from an SD card on the Zyber board transmitted via UART to the VCU118 at an 8 kHz rate and reconstructed using chromatic derivatives at selected midpoints. Reconstructed output was returned to the Zybo and stored back on the SD card. The new architecture supports real-time, continuous signal reconstruction with minimal delay, no post-processing, and works independently of MATLAB, unlike the previous single-window MATLAB-dependent design. In terms of results, the real-time system achieved reconstruction accuracy of around 72.95 dB for real speech and 72.95 dB for synthetic signals, closely matching hardware simulations and FPGA in the loop results. This confirmed the design's accuracy even under real-time streaming conditions. From the resource analysis, we identified DSPs as a critical component in our design, with the initial implementation utilizing approximately 53%, 3,614 DSPs of the available resources on the board. To address this, we focused on optimizing the design to achieve a better balance between accuracy and resource usage. Through word length adjustments and design refinements, we successfully reduced DSP utilization to 26% while still maintaining reconstruction accuracy above 70 dB. Overall, this hardware system successfully performs low latency, high accuracy signal reconstruction using chromatic derivatives with end to end real time performance validated through experiments and hardware tests. In conclusion, we explored applications of CDs in three main areas. Through our results, we demonstrated how CDs can be used for real time signal processing applications in both software and hardware, as well as how they can be used to improve performance and efficiency of machine learning models. We hope this work will inspire future research to explore additional applications and capabilities of chromatic derivatives.